Good morning all, welcome back to the channel. What a load of bull, episode 41. Same week as I filmed the last episode, and I actually filmed a version of this one last night, but I've decided to redo it again this morning in a little bit more detail, and I even made you all some slides. Okay, as I mentioned, if you watched the last video, this week or yesterday, I plan to interrogate the OEM CAN bus network, primarily to find out how to get the ECU master to receive a message when the air conditioning is on. This is important because if the EMU Black or any other standalone ECU isn't aware that the air conditioning is on, then it won't know to do the rev boost to help with idle. Okay, what I've found before I implemented this is if I put the AC on, revs would drop really low and sometimes stall. So yeah, it meant I could only use AC when I was on the motorway, and that's not ideal. We've actually had some pretty hot weeks here in the UK, so this summer I actually jerry-rigged a positive live to an analog input on the ECU, and then I had a switch down here, so when I wanted AC on, I flipped the switch, I got my rev boost, and then I pressed the AC button. So a crude way to do it, and it took up a whole analog input. So I wanted to get away from that. I know that this stuff is all on the CAN bus, so I wanted to work it all out. So that's what I've done this week. It was actually a lot more straightforward than I thought. I was a little bit overexcited last night, and this is pretty technical stuff, and there was a few things which I had total brain fog on, which I probably shouldn't have done. So that's why this morning I've prepared a few diagrams, and I thought I'll go through it at a better pace. Going to do my best to do this in one take because I think I am prepared. So let's make a start. So what is CAN bus? CAN bus is a network, primarily, well, really a network topology. It's made up of two wires, CAN high and CAN low. I've got CAN low in green here and CAN high in blue. Someone who I did some work for years ago said when wiring to use green for low, green like the grass, and white for high, white like the clouds. Now, I don't know whether that was his protocol or general, but convention rather. That's what he did. Couldn't do a white pen, so I've used blue for today. So other examples of networks, if you're in a school or college, you might have used a LAN network. So if we've got, or even in an office, if you've got lots of computers all sharing a central resource, even if it's just internet or a server, these are all going to be connected via Ethernet, and that would be on a star topology. You'll have your router as the central point, router or switch as the central point, and then each device will have its own 8-core Ethernet wire going to it. Okay, CAN bus works slightly different. We've got a bus, and we can think of that as these two along here. All right, that's our bus, and then all of our devices branch off of the bus or tap off of the bus. Okay, what's important about a CAN bus network is you've kind of got two ends to it. It doesn't matter in the physicality where those ends are, but you do need to have two ends to the network. So I'm pretty sure, now I didn't check the manual, we're going to assume that this is how it is in the M35 Stagea. All right, all of these devices are here, but it could be that one of these is the other end. I might have got it wrong, but for the sake of this, let's run with it. So we've got our IPDM, that's the clever fuse box which is in the engine bay behind the battery, ABS module, body control module, which I think is by the driver's foot, TCM by the passenger's foot, dash cluster, and then the OEM ECU. That would be your standard CAN bus network within the vehicle. It runs at 500 megabits rather than a gigabit, which some of the more aftermarket stuff would run at. So if you're running a pure ECU Master install and communicating between their devices, you'd probably use a megabit, or so yeah, megabit rather than, sorry, not gigabit, megabit connection. Or if you're doing it with an AIM ecosystem, Haltech, whatever. But this being an older vehicle, turn of the millennium, it's using 500. So that's what this network runs at. And when we set up the CAN sniffing software in a minute, that's what we'll be setting it up as. Key thing about the ends, I'll go back to that, all right, is they will contain a 120 ohm resistor, and that resistor bridges between CAN low and CAN high. Okay, if you were to put a multimeter on one probe on high and one probe on low and measure the resistance, you should get 60 ohms. Okay, because you've got 220 ohm resistors in parallel. Basically you divide that by 2 and it should be 60. Okay, so a key way if you're ever troubleshooting a CAN bus network is if you do that test and you get 120 ohms, that means that you're missing one end of your network. Okay, you're missing a key part of that bus. This is what's existing here. This is already in the vehicle. Let's say we were setting up a ECU Master PDU, okay, and it's the very first device that's on the CAN network. Okay, we're going to need a CAN to USB device. I'll talk more about that one in a minute. But in order to communicate from the laptop to that, forget all this other junk, we've just got 2 wires going from here to here. I'm going to need to put a physical 120 ohm resistor across CAN high and low there. And then fortunately in my CAN adapter here, I've got a switch to enable that on or off. I'll turn it on. Then I've got my resistor here, got my 2 ends of the network, and I can communicate with one another. It's good practice actually to put physical resistors in, because like I said, say we had an issue where the ECU went down, okay, and it took out that 120 ohm resistor, that means that the whole rest of the network would go down. Whereas if we had a hardwired resistor, okay, if that device goes down, at least there's an end to the network. So what I've done, all part of the plug and play harness which I made a few years ago, the EMU Black taps in off of this bus. Okay, I know that I've got that working already because I've done some stuff with torque reduction requests. So in principle that worked, but it's only this week which I've gone to the trouble of interrogating the existing network to work out messages which I need. And to do that, I used a CAN to USB adapter. Lots of different ones out there. I borrowed this one from work, ECU Master USB to CAN. It's got a switch on it there for a 120 ohm resistor. We don't need it today because we're interrogating an existing network. It uses a serial connector here, and then these are tapped into a little breakout plug which I've got in my loom down there. Cool. I think that's enough on the fundamentals of a CAN bus topology. I'm going to move on to slide 2 now. If you didn't know already, I'm actually a lecturer in a college. And I'm on my summer break now, and I think I might be ready to go back to work. I've gone quite overboard on this video. I do hope you enjoy it. My son's also been away with his mum for a week as well, so I've not been in dad mode. I've literally been me, my laptop in the car for the last week, so apologies if I've got a bit overexcited about this. I want to talk very briefly about the waveform on a CAN bus network, just really to talk about the voltages which are involved. I haven't got an oscilloscope here, so we're not going to be measuring that. Well, you could say that's out of scope from this video. Sorry, not sorry. Anyway, with high-speed CAN bus 2.0, the key thing is we're looking for a voltage difference of 1.2 volts between CAN low and CAN high. Okay, our middle point is going to be roughly 2.5 volts. Okay, so the high edge of low might be, let's say, 2.49 volts, and the low edge of high might be 2.5. So very, very close to one another. But what the CAN bus is looking out for is this difference between the two of 1.2 volts. Okay, that's when it knows, okay, I need to react. There's data there. One thing which is quite important with CAN bus is that we always connect. So if I've got a device on this side, device on that side, we always connect high to high and low to low. If it was serial, you might have T and R, transmit, receive, and then on the other end, you'd have the opposite. But CAN bus, it's always got to be like this one. So that's roughly, if we were to scope it, that's what the waveform would look like. Okay, this message, it doesn't actually mean anything. Okay, I've not been clever. I just wanted to do a basic easy wave, 0 1 0 1 0 1. Okay, if you could only, for whatever reason, say you only had one probe and you had to scope it, if you scope the low one, when you get a high, a positive value, you know that's your 1. Okay, that's a kind of an easy way to think of it, in my opinion. The reason why we have 2 wires is so that if we pick up any interference on the wave, okay, on either wave, chances are the same interference will be picked up on each, because they're not right next to each other, and then the devices can cancel out that interference. Okay, this wire has to be twisted pair. That's all part of how CAN bus works. Cool. I think that's enough on possible wave structure. I'm going to jump into now the light client software, because at the moment that looks scary. Please don't run away. I'm going to explain it in a little bit more detail. So I've got everything set up in ECU Master. We'll come to that in a bit more detail in a minute, because really it all starts with light client. Launch light client. This is what I was talking about, the bit rates. Okay, so I think it will search and kind of work out what's going on here. Aftermarket stuff, race car stuff will probably all be running on 1 megabit, whereas we're going to be running on 500 kilobits. Sorry, I got that wrong earlier. Apologies, I should know better on that one. I already know that's what we're working with, so I'm going to search for that. Okay, the point of this software, really, this is the ECU Master software. This is more for programming and configuring some of their CAN-based systems, such as GPS modules and tire temperatures. But it also does a fantastic job of sniffing and looking for all the messages which are on the network at any given time. Okay, I actually thought that there was going to be more than this. Now, I know that might look a bit scary already, but there's not actually that much there. Okay, if we look at the ID on the left hand side, that is the PID, that is the ID of the CAN message. Okay, now didn't actually take all that long, but if we have a look at, in fact this might not work because I haven't got the engine running, but we'll try it anyway. If we have a look at 35DH, okay, the H is telling us that it's in hexadecimal. So, and we'll talk more about that in a minute. And now if I press my aircon button, as predicted, I need the engine running to turn that on. Oh, no, I can do that here. Hold on. There we go. Yeah, boy. Look at that. Okay. So AC button, we can see a difference there. Okay. The update is 10 hertz, so not very often. That's for the body control module. It's not mission critical stuff. Some of this other stuff will be live data, engine parameters, key things. So yeah, we've now found our message, and we've now found that when that C1 goes to or when that byte goes to C1, we know that that's what we're going to be plugging into our ECU Master software to hopefully figure that out. Cool, right, I'm going to turn this off, jump back to the slides. So let's have a think about that 35D hexadecimal value, okay? Hexadecimal is a base 16 number system. We're used to working with decimal, that's base 10, okay? And we've also got binary, which is base 2. I'm not going to talk about that today, I don't think, in too much. And you've also got octal, but let's not go down that route today. So with decimal, we have 10 individual characters, 0 to 9, okay? With hexadecimal, we have 16 individual characters, which are 0 to F, okay? If we look over here, D column, 0 to 9, okay? In hexadecimal, 0 to 9 is exactly the same. But when we get to 10, if you look, 10 takes up 2 characters, doesn't it? Well, now I can represent that with 1 character. And when we start to look at things like CAN bus messages and using bytes and stuff, it's a lot easier if we're dealing with less characters. So we've got 35DH as that was represented in the Light Client software. Hex is also represented sometimes as X times 35D, or you might see 35D to the power of 16. Okay, so basic hex conversion there. Let's break down what that means. So think of it as units, tens and hundreds, but the hexadecimal version, okay? We use units, tens and hundreds in primary school education in the UK. I'm sure you use something like that in other countries. Do let us know in the comments. It'd be quite interesting actually to know how you do that in other places. So let's put this into a table. You do a similar table like this if you're converting from binary with a 1, 2, 4, 8 column, but we're using hexadecimal, so we've got a base, a 16 to the power of 0, 16 to the power of 1, and a 16 to the power of 2 column, okay? So I've got my D, which is also, if we convert it, 13 in this column, and then I've got 5, 3, okay? If I then think about it, I've got 13 times 16 to the 0, which is 13. I've got 5 times 16 to the 1, which is 80. And I've got 3 times 16 to the 2, 3 times 16 to the 2, which is 768. And if I add those together, bunk to bunk to bunk to bunk, I get 861. Why is this important? Well, ECU Master software uses hexadecimal message IDs. Link software uses decimal message IDs. So if you're working with a different manufacturer, be aware of what value it's looking for, okay? That was a real head scratcher for me when I first did my CAN stuff for the torque reduction, because I was working with a value from a link which was in decimal. I plugged that into the ECU Master software, didn't do anything, but when I converted it from decimal to hex like this, all of a sudden that worked. Whew, big. I'm going to pause it now because I'm about to run out of storage on my phone, so I'm going to go and plug it in, grab a quick swig of coffee, and then come back and explain this first byte that we're looking at. Okay, welcome back. Sorry, had to free up some space. That's really annoying because I was super prepared for this video and I thought I could have done it in one hit, but we've got another 19 minutes and 46 seconds of storage to go. So let's carry on. What we just done was converted, or I showed you what 35D meant in a decimal value, okay? Fortunately, we don't have to do this every time. There's actually quite a few ways to convert this, but it does help if you've got an understanding of what the data is and what each column means. That's what, when I first started working with hex, that's what really took me a while to get used to the column headings, okay? And as you can see, I even got that wrong today, okay? It's not 32, it's 16 to the power of 2, okay? I did it wrong, as you can see, and I didn't get my number, so that was a little edit. So yeah, actually built into Windows calculator, if you change the options up here to programmer, you can actually work with hex. So let's prove the point of 3, 5, D. If we look, decimal is 861, and if we come back to our calculations, 861. Well done, team. Woohoo! So let's jump back quickly to that 35D message. Okay, if you remember, we were looking at that C1, that first byte there, byte 0. That's where the change of state comes in when we press the aircon on. Let me turn that on again, sorry. Yeah, so C1 is changing. I'll just turn the fan down a bit so it doesn't ruin everything. So if we do the same with that here, because that value there, all of those bytes are in hex as well. Okay, you can see some letters flashing around up there. These are always going to be in hex. The data will always be in hex. It's the IDs which will differ from manufacturer to manufacturer. It's the same thing, but it's just a different way of representing it. Okay, like I said, Link seem to do it in decimal, even though a lot of their documentation talks about hex, and they tend to use the representation of X0 rather than the H which ECU Master use. Okay, so if we take that C1 value, okay, or C0, and we plug it into the table again, first column being 16 to the power of 0, 1. Second column being 16 to the power of 1, and it's C. So C, if we come back to over here, C is 12. If I then do the same math, I've got 1, I've got 12 times 16 to the 1, which is 192. If I add the two together, I get 193. Remember that value, and it's actually, there's a little anomaly attached to it. I'm a bit annoyed, but just remember that 193 value. Cool. So let's just flash back to this one. We've got our PID, our ID there. We've got our DLC here, which is telling us how many bytes are in this frame. Okay. We've got the update interval of how often that's getting broadcast. And then that's how many times it's been broadcast since I launched the software. CAN's a funny one. It's a bit like it's a bit of an Aggie network in that every device is just shouting, but only certain devices will listen to other devices, or will only listen. I think they're kind of shouting but have selective hearing. I think that's a good way to think of it, rather than the OSI model, or looking at Ethernet, which is a lot more refined, a lot more dignified protocol with sending requests and confirmations and things like that. CAN bus is just shouting all of this data at once. Cool, so we've got our structure there. Okay, there is more to it, but this is the practical application of it today. We're not going to be looking at the whole wave or the whole frame, just the useful bit for us. So let's go back to the slides. We've got 3.5D. We've got our 6 to tell us that we're expecting 6 things over here. And each of these, starting here, this is byte 0, byte 1, byte 2, byte 3, byte 4. Okay. I'm going to jump into the ECU Master software now. And then I'll come back and explain these bits, because at the moment this probably won't make sense. So in the ECU Master software, if we come up to Tools and User Defined CAN Stream, this is where we can set up send and receive messages, okay, when we're attached to a CAN bus network. This is where you would configure a dash, I think, if you're working with that. I've already got a couple in here. One of them is for my torque reduction request. One of them is my gear position when in manual mode. And the message 3 is what we've set up today. So if I open that one, oh no, if I double click that one, okay, here's what it looks like. what is the message ID? Well, I'll just turn the fan off, sorry. We already know the message ID. Okay, we've sniffed that out. The DLC was 6. It is a receive message. What are we expecting to see in this message? What's going to make us happy? Well, byte 0, we're looking for C1, aren't we? That message has a 5-0 next to it, and the rest were 0 zeros. Okay, so we put that data there into the CAN message, and then we find the mouse. There we go. Sorry. Then we need to set up what we're going to do with that message. So channel is in the ECU Master software. What are we going to be defining this CAN message as? Now, for me, it made most sense. I've done it. Oh, I better, careful. What's really annoying, I kept doing this yesterday. If you close one, it resorts back to message 1 up here. So I need to keep going back to message 3. Don't want to see that. See, watch this. If I click OK, it goes back to message 1. But I want message 3, so click it once. CAN analog 8. There we go. So let's have a look at this. Log channel is what the ECU Master is going to see it as. So these are all the things I have available. This is what I'm limited to. CAN analog, CAN switches, GPS speed, and wheel speed. Okay. These are the predefined headers. That's all I have. Other manufacturers, you might be able to use temperature, things like that. Do bear in mind though that there is a whole ECU Master ecosystem for things like tire temperatures, EGTs, things like that, and they will have their own things pre-set up, embedded in. But what we're working with is simulated analog signals or simulated switch signals. Gone for analog 8 because that's at the other end of the things that I've been working with already. Byte position is talking about in this message, which we set up here, what byte are we looking for? And we're looking for byte 0. That's C1. Okay. Then we've got some settings. And again, I had to do a bit of a refresher on this morning to get my head around it. We've got a multiplier, a divider, and an offset. What this is saying is when this message is being broadcasted by its existing broadcast device, its source, it's been multiplied, the value has been multiplied by 100 and it's been divided by 1. That's the best way that I can describe it. So that means that if we are receiving that message, we need to do the opposite. This is where it gets a bit confusing. So I need to take that message, that 193 that we calculated, okay, and I need to, my divider is 1, so 193 divided by 1, nice easy math, is 193, and then my multiplier is 100, so 193 divided by 100 equals 1.93, and that's a really nice number because that's within our 0 to 5 volt or our 0 to 12 volt range, and a CAN analog channel on ECU Master is 0 to 5 volts. Now if I move that out the way slightly, okay, and click OK on that one, and I'll need to turn the fan back on again, sorry. If I press the button on and off, you can see when it's on I get 1.96 volts, and when it's off I get 0 volts. What I'd really like to have seen, and I'm sure that that's what you're expecting, is 1.93. So somewhere we've got a difference of 0.3 volts. I'm not sure how that happened. Last night, before I'd actually got my head around it, I just juggled different numbers in multiplier and divider, and this was the best set of states which I could get as 0 when it's off or a decent positive value when it was on. Had it come through as 193 or 1.93, that would have been amazing. Now I then plugged that into the AC settings, okay, in the activation input, but it didn't seem to be enough of a voltage change for that. So when I had this working before, it worked with a real 12-volt signal on a real analog. This that change there wasn't enough. So what I've had to do is run it through a virtual output. And what the virtual output does is it takes the input, CAN analog 8 in millivolts, because we are working with 1.9 volts or millivolts. And we're saying when it gets greater than 100 millivolts, react, flip that state. And we can see that if we come over here and look at the log, okay, it will come through in a minute. Some of this is off the page. There we go. If I toggle it, then you'll be able to see it as it comes through. But you can see CAN analog 8 on, and then this virtual parameter, this virtual output also on. What's not happening at the moment is AC. It's not being triggered because the engine's not running. So just to prove that that all works, if I now start the engine and try and get all of those in frame, we got AC. Oh, so pleased with that. So pleased. Like I said, I did have that set with an analog input. I had tried it with a ground switch, but that didn't work. It needed an analog input. But to me, that's a waste. And when you've got a degree in networking and you teach this stuff, you should actually figure out how to do it properly. And that's what I've done. Cool. I hope you've enjoyed that. I enjoyed putting that all together. I really like this kind of stuff, if you hadn't noticed already. I mentioned that I lecture, so I work in engineering. I run a motorsport engineering degree course, and I teach electronics, robotics, PLCs and automation to a number of different programs. So a lot of it is all very similar in terms of sensors, process, output. So I'm either programming a race car, a conveyor belt system, or a robot. It's all very similar. So that's why I know quite a bit about this, and being able to apply all of my kind of industry experience in the electrical industry when I was on the tools, my degree and my love of cars. That's where the whole motorsport electronics and especially the CAN bus stuff I really get excited about. So what am I going to do next? I've already got this torque reduction request set up. I originally, and I've shown it in previous videos, I had a custom table whereby when that message came through, it retarded the ignition by a little bit. There's actually better strategies built into the EMU Black. I was trying flat shifting, but I don't think I've done a lot of reading on it last night, and I think gear cut is going to be a better one for me. So at the moment, I've only got an input of when it wants to change gear or when it wants to reduce torque, not whether it's an upshift or a downshift. So I'm going to spend some time in Light Client playing with the gear shifter, maybe go for a drive if I can find someone. Unfortunately, my son's only 11, so he can't drive the car for me. And although he has helped me, he was absolute star tuning the LPG multiplier the other day. I think looking out for changes in hex values is a little bit beyond him at the moment, but maybe after he's watched this video, he'll be keen on it. We do binary. Cool. Right. Thank you for watching. I hope you liked the title of the video. I thought that was quite funny. I'm going to make you a deal here. If you're a student, okay, if you're a student of mine or you're studying somewhere else and you've used this video, okay, it would be relevant in IMI EE3 and MS90, that's electronics and also data acquisition, and on our degree program as well. Obviously we do data acquisition, you do electronics in your second year and stuff like that. If you found this useful and you reference the channel, the video title to the correct referencing standard of your academic institution, my guys, that's Harvard, and you send me evidence of that, so I want to see what a load of bull, M35 Stagea sniffing lines of CAN bus. If you can show me evidence of you referencing that in one of your papers, in one of your submissions, I will send you a prize. Don't know what it's going to be, but I'll put that out there for all the students and academics if you found this useful. So thanks a lot for watching, guys. Don't know when the next video is going to be now. I go back to work next week. If I make any more breakthroughs with the shifting and things like that and all of this jazz, I'll let you know. But at the moment, I think that's it. So if you like the video, please give it a thumbs up. If you're enjoying the content on the channel and you haven't done already, please subscribe. Any questions, if you need any help or whatever, please reach out, put some comments below. More than happy to help where I can. All right, guys, have a good day.